So, a very good evening to all of you present here. Myself, my name is Ankit Kumar, and I am a assistant professor in the Department of Mathematics at Chandigarh University. So, basically, in today's lecture, I will discuss about some preliminary concept of the Riemann integrability, Riemann integration. After that, what are the Riemann's integration? What are the conditions for Riemann integrability? And after that, link to this concept Riemann integrability to the Riemann stieltjes integral. Because Riemann stieltjes integral So basically, what is the definition and existence of the Riemann stieltjes integral? Okay. So basically, in this section, I will talk about the definition, existence, and the concept of the Riemann stieltjes integral. Okay. After that, we will discuss about what are the conditions of the RS integrability, what are the conditions of RS integrability, and some theorems, theoretical part from theorem. So theorems is also discovered by in this part. And after that, properties of the integral. What are the main properties of the integral? And in last section, I will discuss about the integration and differentiation part of the course. So first of all, I will discuss the Riemann integral. What is the Riemann in Indian? What is the Riemann integral? So basically Riemann integrable is nothing but it is a integral. It is the integral which is beyond the scope of the simple integration. It is beyond the scope of simple integration. Because here it is said that let a comma b be a given interval by a partition P of a comma b being a finite set of points. So first of all, we draw a line. Okay, this is A and this is A and this is B. Okay, so this is A and this is B. After that, we will divide it in some finite number of points x0, x1, x2, up to the order of xn minus 1, and xn is equal to. So first point x0 is equal to A, and second one is equal to xn is equal to B. So the dividation of this interval in the finite number of the points is said to be the partition P of A comma. So what is the partition P of A comma P? The dividation of the interval into finite number of the points is called the partition P of closed interval A comma. Okay. So here some points delta xi. What is the delta xi? Delta xi is nothing but xi minus 1. This is xi and xi minus is the delta xi. Okay. So suppose here are 2 points. Here are 2 points xi and this point is xi minus 1. xi minus 1. Okay. So this is xi and this is xi minus. Okay. So we define delta xi. Delta xi, this the difference between these two consecutive points. These two consecutive points is delta xi. Okay. So first of all, we take a closed interval. After that, we divide into a finite number of the subintervals. These finite number, the dividation of these finite number of intervals is called a partition of closed interval a comma b, and there are a finite number of the subintervals is also exist in the closed interval. Meaning thereby this is x naught comma x1. So this becomes a closed interval. So this becomes a closed interval. So there are finite number of the subintervals also exist in the closed interval a comma b. So we pick 2 points xi and xi minus 1, and we denote this by delta xi. Okay, we pick 2 points in between of these subpoints of the interval closed interval a comma b, and we choose these 2 points xi minus xi comma xi minus 1, and the difference between these 2 points is said to be the delta xi. Now we define capital Mi. What is the capital Mi? Suppose between these points xi comma xi minus 1, here some point x exists. Here some points x exists. Okay. In between of these points xi comma xi minus 1, some points x exists. And if we define a function f, if we define a function f at that point, so at that point, so the supremum value of f, the supremum value of f at that point is known as capital. So first of all, understood this concept. What is the capital M? So capital Mi is nothing but if we divide the closed interval a comma b into a finite number of subintervals, and if we pick 2 points xi minus 1 comma xi, and we choose a point x between these 2 points, and we define a function f at this point, then the supremum value of f at x is known as the capital Mi. Is known as the capital. And in a similar manner, the infimum value or the minimum value of fx, the minimum value of fx at the point x, is known as the small mi. Is known as the small mi. So capital Mi is nothing but the supremum value of fx at the point x, which lies between xi minus 1 comma xi, and the small mi is nothing but the infimum value of fx at the point x, which lies between xi minus 1 comma xi. Okay. So after using this concept, what is the UPF? UPF means upper Riemann sum. UPF means what is UPF? U P comma F is nothing but upper Riemann sum. So upper Riemann sum. Sum means summation. Sum means summation. So summation I is equal to 1 to n. Upper Riemann sum means upper bound. Upper Riemann sum means upper bound. So upper Riemann sum, this is Mi. Mi is nothing but supremum of fx at the point x, and delta xi is nothing but the xi minus the difference between the 2 points. So if we sum this, I is equal to 1 to n, meaning thereby this is capital Mi M1, okay, delta x1, M1 delta x1, okay, then plus M2 delta x2, then plus M2 delta x2, m2, we expand this m2 delta x. And this is LPF. LPF. So if we add this m1 delta x1, m2 delta x2, up to dot 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 mn delta x. So the sum part is defined as the upper Riemann sum. Upper Riemann sum. Upper Riemann sum. And upper Riemann sum is nothing but the summation of the supremum of fx into delta x1. Okay, so what is the delta x1? Delta x1 is x1 minus x1. If we put x1 here, so delta x1 is this delta x1. What is delta x1? So delta x1 is, if we put I is equal to 1, then this is x1 minus x1. x1 minus. Okay. So x1 minus x0. If we put delta x2, so this is 2 minus x1. So if we sum all the finite sum, we sum all the finite product of mi into delta xi, then this summation of this product is called the upper Riemann sum. Upper Riemann. And in similar way, if we take the sum of mi is nothing but the minimum value of fx at a point x, which lies between xi minus 1 to xi, and multiplied by the delta xi. Delta xi is nothing but xi minus xi minus 2. So this is upper Riemann sum and this is lower Riemann sum. This is upper Riemann sum and this is lower Riemann sum. So I hope this concept is clear to all of you. What is the upper Riemann sum and what is the lower Riemann sum? Okay. So I repeat this concept again. So if we take a closed interval a comma b and we define a partition P of closed interval a comma b, if we divide this interval into finite number of the subpoints, okay, and if we divide the finite number of the subpoints x1, x2 up to dot dot xn minus 1 comma xn, then there exists a finite number of the subintervals also, which takes in the form x0 comma x1, x1 comma x2, and so on. Okay, and after that and after that and after that we define delta xi. Delta xi is nothing but if we divide this interval into finite number of subintervals, then we pick 2 points anywhere between this xi comma xi minus 1. So the difference between xi minus 1 is delta xi. Okay, after that we define mi. What is the mi? So mi is supremum of fx, where x lies between xi minus 1 to xi. So if we take any point x between xi to xi minus 1, then if we define the function f at this point x, then the supremum value of f, at this point x is known as capital, and the infimum value of f at that point x is known as small m. And based on this concept, mi, capital Mi and small mi, we define the upper Riemann sum, lower Riemann. So upper Riemann sum is nothing but the summation of the supremum value of fx into delta xi, and the lower Riemann sum is mi, and infimum value of fx into delta x. So if we sum this product into a finite number of points, means I is equal to 1 to n, then we get the upper Riemann sum. And in a similar manner, we get the lower Riemann. Okay. Now we will move the next slide. What is the upper Riemann integral and lower Riemann integral? What is the upper Riemann integral? So First of all, if we found up comma, if we find up comma f from I is equal to 1 to n mi into delta x. So if we take the infimum of this upf, if we take the minimum value of this upper Riemann sum, suppose we observe some values -1, 0, 1, 2, 3. So we take the infimum of this. We take the infimum of this. So the infimum of this is -1. Infimum of this is minus. So this -1 is the value of the upper Riemann integral. A integral from a to b bar. This is upper Riemann integral. And upper Riemann integral is nothing but infimum of this. So basically in the Riemann integral, we find the integration of some abstract areas, such as area is this type. So we take the simple integration is not possible. So we calculated the Riemann integrability. And Riemann integrability is the sum of that points, that curves. Okay. So if we sum these points, then we form the area under this. So basically Riemann integrability is the why we use the Riemann integration in place of the simple integration, because in simple integration we define some area, the specified area, but in the Riemann integrable we cover the area which is abstract, which is not fully defined. So we covered, we calculated these areas, okay, and after that we summing this sum and we obtain the actual area of the curve. Okay, so this is the infimum value of up comma f. And in a similar manner, if we take the supremum of this LPF, lower Riemann sum, if we take the supremum of this lower Riemann sum, then we obtain the lower integration, lower Riemann integral, okay. So if we obtain this, if we take the supremum value, first of all we obtain -1, 0, 1, 2, 3, and in this set, if we take the supremum value of lower Riemann sum, that is 3, then this 3 is the value of the lower Riemann integral. Okay, so from equation 7 and 8, we can say that the value of the Riemann integral, is integral from a to b fx dx is equal if the upper Riemann integral is equal to the lower Riemann. Okay, suppose you obtain the infimum of 1 in the upper Riemann sum, and we also obtain the supremum of lower Riemann. So if both the values a closed interval a comma b, integration from a to b bar and integration from a bar to b, if both these integrations are equal, then we denote this by a common symbol called integration from a to b fx dx, and which is known as the Riemann integral of f over. So first of all, what is the summary of the Riemann integration? The summary of the Riemann integration is that first of all we take a closed interval. After that we divide to a finite number of subpoints, and in the subpoints we make some finite number of the subintervals, and after that we define capital Mi and small mi. So capital Mi is nothing but supremum. Capital Mi is nothing but supremum of fx at a point x, which lies between xi minus 1 to xi, and small mi is infimum of fx at x is equal to xi minus 1 to xi. After that If we take the summation of these two products, then we can obtain the upper Riemann sum and lower Riemann sum. So the infimum of upper Riemann sum is the upper Riemann integral, and the supremum of the lower Riemann sum. Supremum of the lower Riemann sum is the lower integral. And if the upper Riemann integral is equal to the lower Riemann integral, then the combination of these two is denoted by integral from a to b s, which is the Riemann integral. So this is the preliminary concept. This is the preliminary concept, and this is the preliminary notation symbol which we cover, and which are, and the combination of these symbols are known as the primarily concepts of the Riemann integral. So I hope this concept is clear to all of you. Now we will move the next part, which is most important topic of this discussion, that is the Riemann stieltjes. So what is the Riemann stieltjes? Riemann stieltjes integral. So क्या बोलेंगे? The Riemann stieltjes integral. Riemann stieltjes. Basically, this is the extension of the Riemann stieltjes. Basically, this is the extension of the Riemann stieltjes integral. Okay. So basically, this is the extension of the Riemann stieltjes. Now, what is the definition of this Riemann stieltjes? So let first line. Let's look all of you. First line. Let alpha be a monotonically increasing function on two-dimensional rate. Since alpha A and alpha B are finite, it follows that alpha is not corresponding to each partition P of two. So first of all, alpha be a monotonically increasing function. Suppose this is a line. This is a monotonically increasing alpha. Okay. This is a monotonically increasing function. Suppose okay, so this is an alpha curve. This is an alpha curve which is monotonically increasing. Which is monotonically increasing. Which is monotonically increasing. Monotonically increasing. Mi means monotonically increasing. Suppose this, if we denote this line by the interval, this is a comma. This is a comma. So this point is A, and this point is okay. So in the definition, it is given that alpha be a monotonically increasing. So if we construct this alpha 1 point, 2 points, 3, 4, 5, 6, and so on. There are finitely many in the closed group. And these points are x0, x1, x2 up to dot. And again we pick 2 points xi. Again we pick 2 points xi, and this is xi minus 1. Xi and xi. Okay. So in between of these points, there are many points. There are many points lies in between of these two intervals. There are many points lies between in this subinterval. So alpha is monotonically increasing function. We divide closed interval a comma b into a finite number of the subintervals. Use the primarily concept of the Riemann integration. We pick 2 points xi minus xi comma xi minus 1 comma xi. Okay, so here it is scanned that let alpha be a monotonically increasing function on K of closed interval. Alpha and alpha b are finite because this is a finite interval, so alpha and alpha b are finite. Bounded on closed interval will be true. Closed interval is always bounded to closed. Okay, so this is also a bounded interval corresponding to each partition P of closed comma b, right? So basically, we divide this interval into finite number of the subpoints. Then in this interval, a partition P also exists. A partition P also exists. Now we will define this delta alpha. So in similar manner, uh, we define delta xi. So delta xi is xi minus 1, xi minus xi minus 1. So here we operate delta alpha and delta alpha is alpha xi and alpha xi minus 1. So if we operate this alpha on these points xi and in these points xi minus 1. Okay. So the difference between alpha xi minus alpha xi minus 1 is nothing but delta. Is delta. So I hope from this it is clear that what is the alpha. First of all, we take the interval, we divide it into finite number of some intervals. Secondly, we take a monotonically increasing function, which is a curve, nothing but curve. So, and we pick 2 points xi, comma xi minus 1 in between these two intervals, and we define the distance between or the difference between these two consecutive points and denote it as delta alpha I. Okay, now we will move to the next part. It is clear that delta alpha I is greater than or equal to 0. Okay, because this is a monotonically increasing function. Monotonically increasing function. So monotonically increasing function, meaning thereby delta of alpha is always greater than to 0. Monotonically increasing function means this x square. X square is also monotonically increasing. So if we put points 1, comma 2, comma 3, okay. So we obtain the value 1, comma 4, comma 4, comma 9. So this is always delta alpha I always greater than or equal to 0 because this is a monotonically increasing function. Delta alpha I is greater than or equal to, okay, because of the property of monotonically increasing function. Now, for any real function f, suppose we take any real function f in between. What is the real function? This is the real function. Okay. So this is a real function f. Now we define which is bounded on closed interval. Which is bounded on closed interval. So this is a bounded function in between the intervals closed interval a comma b, and we put this u p comma f comma. This is upper Riemann stieltjes sum. Upper Riemann stieltjes sum. Okay. So upper Riemann stieltjes sum is nothing but summation. Again, we use the concept of the Riemann integral. Take the summation. Then what is mi? So capital Mi is nothing but it is the supremum of fx, supremum of fx, and where x belongs to alpha xi to alpha xi minus. Similarly, the lower Riemann stieltjes sum, lower Riemann stieltjes sum is mi into delta alpha. What is the mi? Mi is nothing but infimum value of fx where x lies between alpha xi minus alpha xi minus. Okay. So if we take the product of these two into a finite number of the points, after that we sum each of the product, then we obtain the value of the lower Riemann stieltjes sum. Okay, and upper Riemann stieltjes sum is the summation of capital Mi into delta L. Capital Mi is nothing but supremum of fx, where x belongs to alpha xi, comma alpha xi minus. This is alpha. Okay, so this is upper Riemann sum, and this is upper Riemann stieltjes sum. Upper Riemann stieltjes sum, lower Riemann stieltjes. Okay. So upper Riemann stieltjes sum, and with the help of the upper Riemann stieltjes sum and lower Riemann stieltjes sum, we prove that what is the definition, what is the actual upper Riemann stieltjes and lower Riemann stieltjes. So here it is written as capital Mi is nothing but supremum of x, and small mi is nothing but infimum of x, where xi lies between xi minus 1 to xi. After that, if we take the infimum value of this upper Riemann sum, upper Riemann stieltjes sum, if we take the minimum value, here we take the minimum value. We will take minimum value. This is the minimum. If we take the minimum value of this, then this is nothing but upper Riemann integral. Upper Riemann, upper Riemann stieltjes, upper Riemann stieltjes integral. Upper Riemann stieltjes integral. So if we take the minimum value, and what is the lower Riemann stieltjes? This is the lower Riemann stieltjes. So lower Riemann stieltjes is nothing but this is a maximum value. This is a maximum value. Maximum value. Okay. So if we take the minimum value of upper Riemann stieltjes sum, then we obtain the upper Riemann integrable. We take the maximum value, supremum value of lower Riemann stieltjes sum, then we obtain the lower Riemann stieltjes integral. So basically, what is the integral? Integral means the summation of area under the curve. Summation of area under the curve. So in a similar manner, we obtain what is the Riemann stieltjes integral and what is the lower and upper Riemann stieltjes integral. So if we sum the areas of the curve, suppose we obtain the this curve, we obtain the area of this curve. So there are many points. There are many points like this. Okay. So the lower value. So the area under these curves, the area under this curve is obtained by upper and lower Riemann stieltjes. Okay. So after that, actual value of the Riemann stieltjes integral is obtained by equating these two. So the value of the actual Riemann stieltjes integral is obtained by equating these two. So if equation 15 and 16 are equal, this equation is 15 and 16 are equal. Both the upper Riemann integral and lower Riemann stieltjes integral are equal. The upper Riemann stieltjes integral and lower Riemann stieltjes integral are equal. Then we can say that this is the Riemann stieltjes integral of f over cosine over 2 pound. Over cosine over 2 pound. So in this theory, in this discussion, mainly the concept of this alpha. First of all, we take the alpha function. This is a monotonically function. Then divide which total to find the number of the subpoints. These points are called the partition of closed interval A, comma B. Then we define delta alpha is alpha xi minus 1 into this. After that, we define the upper Riemann sum, and upper Riemann sum is what capital M into delta alpha is capital M is equal to table of f(x) at a point x, which lies between xi minus xi minus 1. In a similar manner, we also define Riemann sum, and Riemann sum is M into delta L. And with the concept of the upper Riemann sum and lower Riemann sum, lower Riemann stieltjes integral, we define the upper Riemann integral and lower Riemann. And if both the upper Riemann integral and lower Riemann integral are equal, then the combined value of this is called the actual Riemann stieltjes integral. Called the actual Riemann stieltjes integral. Now, we will move to very important concept of the refinement. What is the refinement? What is the refinement? So, what is the refinement? The partition P star is a refinement of P if P is the subset of P star. Given two partitions P1 and P2, P say that P star is their common. What is the meaning of the actual meaning of the refinement? What is the actual meaning of it? Suppose P is any set, P is any set or any interval which contains the point 1, 2, 3, 4, and 5. We understood this concept by with the help of the example. What is that? Now, suppose we take this P star, P star, and we define this P star. So here, 1, 2, 3, 2.5. It may be possible that between 2 and 3, 2.5, 2.8, 3, 3.5, 4, and 3. Okay. So the partition P star is a refinement of P if P is the subset of P star. P is the subset of P star. So the partition P star is a refinement of P if P is the subset of P. From this example, we can say that P, this is P is the subset of P star. This is P is the subset of P star. P is the subset of P. Because P is the subset of P star. And we also make a refinement P star with the help of the P. But there are more points as compared to P. So P star is said to be the refinement of P. P star is said to be the refinement of P. Given two partition P1 and P2, we say that P star is the common refinement. If we take the interval this P1 and this P2, so P star is nothing but their common refinement. P1 and P2 are the two partitions, then P star. Suppose P1, what is the P1? P1 is 135, P1 is 1, 3, 5, and T2 is 2, 5. Is 1, 5 or 2, 5. 1, 2, 5. So this P starts the common refinement of 135 and 125 because it covers all the points between these 3 points 135 and 125 because 1, 2, 2.5, 2.8, 3, 3.5, 4.5, etc. All these points lies between. So what is the P? P is the partition. P star is the refinement. P star contains 4 points. Then P and it belongs to the partition. It is never beyond the partition because the points 2.5, 2.8, 3.5 are in between these points because the partition is nothing. Partition is nothing but the partition of the intervals. Division of the finite number of the x0, x2, x5, x6, x7 up to 12. So what is the partition? Partition is the division of the interval in finite number of the intervals. And what is the refinement? Refinement is the some more points of the partition, and partition is always the subset of the refinement. And there are more possibilities that refinement is the union of the two finite number of the partitions. I hope this concept is clear to all of you. What is the partition? What is the refinement? Now we will move the next theorem of the Riemann stieltjes integral. What is the Riemann stieltjes integral? So Riemann stieltjes integral is nothing but this. Riemann stieltjes integral is integration from a to b is less than or equal to from integration from FD. Okay. So what is the FD alpha? What is this? This theorem says that the lower Riemann sum is upper Riemann integral. Upper Riemann stieltjes. Upper Riemann stieltjes integral. Upper Riemann stieltjes integral is always greater than or equal to lower Riemann stieltjes integral. This term says that this. First of all, I hope that you should clear the statement of the term that upper Riemann stieltjes integral is always greater than or equal to lower. Now we will move the proof of this theorem. So let me start with a common refinement of the two partitions P1 and let me start with a common refinement. Suppose there are partitions and we divide another two partitions P1 and P2. So P star is the common refinement of P1 and P2. Okay. So first of all, we define this with the help of the definition of the refinement because we say that P is always the subset of P star. Let's say that it's the subset of P star. So if we divide this partition into two finite partitions, P1 and P2, then P1 is the P1 is the subset of P star. P1 is the subset of P star. Okay. So P1 is the subset of P star. So LP1 comma F is less than or equal to LP star comma F comma F alpha. Meaning thereby lower Riemann stieltjes sum is always less than or equal to sum over the parties over the refinement. And this refinement is always less than or equal to the upper partition, upper stieltjes partition. Okay, no problem, Hema. We will cover this. So first of all, we define what is going on. What is going on? What is going on? Meaning thereby this P is the subset of P star because P star is the refinement and refinement is always greater than the partition. Secondly, we divide this partition into finite number of two partitions P1 and P2. So if P is the subset of P star, then always P1 is also the subset of P star. So this concept is now we will move this. This lower Riemann stieltjes sum over the refinement P star is always less than or equal to upper Riemann stieltjes sum. Okay, and this is less than or equal to upper Riemann stieltjes sum over the partition. Over the partition. Now, with the help of the refinement, we take these two concepts. LP1 comma alpha, which is the lower Riemann stieltjes sum, is always less than or equal to upper Riemann stieltjes sum. Upper Riemann stieltjes sum. Now, if P2 is fixed and the supremum is taken over all parts, if we take the supremum, here we take the supremum. Okay, if we take the supremum, then supremum, what is the supremum value? The supremum value of lower Riemann sum is lower Riemann stieltjes integral. So this is the lower Riemann stieltjes integral is less than or equal to P2 F comma alpha. So this proves the first part. Now, if P1 is fixed in this construct, if we take P1 in place of P2, if P1 is fixed and the infimum is taken over all P2, यहाँ पे कर दो P2 and in place of supremum we take infimum. So we obtain that LP1 comma alpha is less than or equal to upper Riemann stieltjes integral. Here we obtain this A into A upon B is less than or equal to L P1 comma P1 comma F comma L. Okay, so from this line we obtain this integral. From this line we obtain this integral. So if we put these two integral in place of this, we put this two integral in place of this. So we obtain the value of. So we obtain the value of. So first of all, we take the refinement. we divide the partition P into P1, P2. We define this inequality, we define this equality, and after that we take these 2 points LP1, alpha, which is Riemann sum less than or equal to Riemann sum. Then take this condition: if P2 is fixed and supremum is taken over all P1, and if P1 is fixed and infimum is taken over all P2, then we obtain the value of the upper Riemann sum and upper Riemann stieltjes sum and lower Riemann stieltjes sum in the form of the upper Riemann stieltjes integral and lower Riemann stieltjes. And if we put these two values in the equation 21, then we obtain the value of this, which says that the upper Riemann stieltjes integral is always greater to lower Riemann stieltjes integral. Okay, I hope this theorem is clear to all of you. Now we will move the next very important theorem of this concept, this lecture. This theorem says that theorem if f is continuous on to then it comes to alpha equals to something. So if f is continuous, if f is continuous on closed A comma, then f belongs to R alpha on closed A comma. Okay. Now suppose in universe all the type of the continuous function are the Riemann stieltjes. First of all, you remember this point. All the continuous functions exist in the universe are the Riemann stieltjes. So continuous, all the polynomials are continuous. Sin alpha, cos alpha, f(ix), multiplication, sum of the functions, product of the functions, division of the functions, and algebra of all the functions are continuous. So if all the functions which are continuous, then these functions are Riemann stieltjes. So basically this term is this part. Basically this term is this part. Now we will prove this theorem. So let us suppose let epsilon positive be given. Okay, let epsilon positive be given. Choose eta positive be any number. Okay, I first of all epsilon positive be given. Eta positive is so that alpha b minus alpha m, eta is less than 2 epsilon alpha be a positive here. Okay, and alpha is a monotopic integral. Mi. So that is Riemann increasing function. To the real analysis with the help of the graph, then it is very easy because real analysis is the part of the graph. So if we analyze anything and theorems and statements with the help of the graph, then it is basically visualize what is going on, what is happen. So basically alpha is a monotonic. So alpha b minus alpha n is less than 2 epsilon and epsilon is positive. So basically this is statement, reciprocity is clear. Now since f is uniformly continuous on closed and if it is a monotonically increasing function, then this is a uniformly continuous. So if it is uniformly continuous, so with the help of the definition of uniformly continuous, what is the definition of the uniformly continuous function? What is the definition of uniformly continuous function? So equation 24 is the basically the definition of uniformly continuous. If mod of fx minus ft is less than 2 eta, where x minus t is less than 2 delta, then f is said to be at fx is uniformly continuous, meaning thereby if f of n n and bn any sequence of n f of bn to f of n tending to modulus value tending to 0 as mod of n minus dn tending to 0. Then f is said to be a uniformly continuous. So first of all, we define this in a similar way. If an minus bn tends to 0, this implies and implies that f of n minus f tends to 0. If this condition is satisfied, then you can say that function is uniformly. So basically, this is the difference. Now we will move the next line. Now we will move the next line. P is any partition of a quantity such that delta xi is less than to delta for all. No problems there. No problems there because P is any partition of closed interval account. So if you divide the intervals into finite number of the same interval, the delta xi is less than to delta for all I. And this is capital Mi and minus small mi is less than to capital Mi and minus small mi is less than or equal to eta. Less than or equal to eta. Now, ut comma alpha minus lp comma alpha is so this mi. What is mi? Mi is the supreme. What is the mi? Mi is the supremum of fx. You define in the above slide. Mi is supremum of fx at x lie between xi minus 1 to x, and small mi is the infimum of fx. So supremum value minus infimum value is less than or equal to eta. It may be possible. No problems there. May be possible. Capital Mi is the upper Riemann sum, small mi is the lower Riemann sum, and we apply this. Upper Riemann sum is, what is the value of the upper Riemann sum? Capital Mi into delta alpha. Okay, and the value of lower Riemann sum is small mi into delta alpha. Okay, this concept is also clear. So if we take the difference between UPF from alpha minus LPF from alpha is nothing but mi minus alpha into delta alpha. Okay, and this alpha is less than or equal to eta into delta alpha, and delta alpha is nothing but this from this, and by theorem, if up comma alpha lp comma alpha is less than to epsilon, then f is nothing but f belongs to the Riemann stieltjes integral. F belongs to the Riemann stieltjes integral. So basically, we prove the theorem with the concept of the Riemann stieltjes integral. What is the partition? What is the lower Riemann sum? What is the upper Riemann integral? Lower Riemann integral? What is the upper Riemann integral? What is the uniformly continuous? What is the continuous concept? Basically, this is a primary concept of the. So again, if we discuss this, first of all, alpha is any monotonically increasing function. So alpha b minus alpha x is always positive. So we take this same to since f is uniformly continuous on two diagram. So we use the definition of that's not this is if P is any partition P of that is delta xi, then capital Mi is supremum of x, small mi is the infimum of x, where x lies between x and y. Now we use the definition of comma alpha minus lp comma alpha, and that's simply. So this is capital Mi minus small mi into delta alpha, and the value of mi and small mi, so we put this value in the from the equation 25, and 20 from the 25 it is given that this is eta, this is eta, this is delta alpha, and if we take the sum of this delta alpha, delta alpha, delta alpha, delta alpha, so this is nothing but an end point and first point. End point, this is a, and this is a point, and this is a. Basically, the alpha is delta b minus delta alpha a plus that. Phi theorem belongs to graph. Now, we prove the next theorem. If f is monotonic on post-monotonic and if alpha is a continuous. So this is also a very important concept. If f is a monotonic function, monotonic on post-monotonic and alpha is continuous, so f belongs to f. This is a concept. Suppose alpha be a given for any constant integer, you choose a partition such that this we make this constant alpha delta alpha will equal to alpha b minus alpha I is equal to delta 2. This is possible since alpha is continuous. It is given that alpha is continuous, so it is possible. It is possible, no doubt. We divide the partition into five. We suppose that f is monotonic increasing. Suppose monotonic increasing. Monotonic increasing means this. This is a monotonic increasing function. Now, this is capital Mi fxi. We define this capital Mi with fxi, and this Mi is fxi minus 1. Because here we take xi minus 1, then we take xi minus 1, and here we take xi. So, capital Mi is the always fxi and is always fxi. Now, we take the difference of the upper Riemann stieltjes sum and lower. Upper Riemann stieltjes sum and lower Riemann stieltjes sum means mi into delta alpha I and small mi into delta alpha I, and in place of mi we put fxi, and in place of fxi we also put fxi. So if we take the difference between this, then it is always less than 2 epsilon. Epsilon. So if up comma alpha minus alpha alpha is less than 2 epsilon, then by theorem f belongs to mean value f is nothing but alpha very much still this sum. This still this sum. So basically in this lecture I will cover the basic concept of Riemann stieltjes integrals, Riemann stieltjes sum, partition, refinement, monotonic function, what is monotonic, and many more. I hope all the concepts are clear to all of you. I try my best to understand you, all of you present here. So basically in this slide, I will cover the Riemann integral and Riemann stieltjes. And in the next session, I will cover the first and second integral theorem and the fundamental theorem of the calculus. And after that, I will make the uniform convergence, which is very most important topic of the real analysis. So basically, in the next class, I will cover the fundamental theorem of calculus and first and second linear theorem. Okay. So if possible, then I will cover some more normal examples in which you understand what is going on, what is the relation here. So and some problems which we will solve in the next session. This session, I will wind up this session here. Sumitra Das, hello sir, when we will get the PDF. This PDF material I will discuss with the administration, and if possible, then I will inform you what is the process of getting this type of the PDF. And if I will forward this PDF material to the administration, and if we allow, then I will also give this PDF to all of you. So I will talk to this topic in the next session after uh, communicating this topic with the administration. So thank you very much for listening me carefully, and I hope this session will be very enjoyable to all of you. So thank you very much.